So thank you, Chairman, for your introduction, and good morning to everybody. So in my presentation, I would like to talk about a complex system for contactless interrogation of resonant sensor. And this is the outline of my presentation. I have a brief introduction of a resonant sensor, then I show you the proposed time-gated contactless interrogation. Then I move to validation of principle and some experimental results, and then I move to the conclusion. So resonant sensors are well-known devices that they can sense physical quantities and biochemical quantities by adopting the proper sensitive layer. And those quantities affect both the mechanical resonance frequency of the sensor and the quality factor Q. And the common way to measure these devices is to use impedance measurement and feedback oscillators, but of course we can achieve to a contactless interrogation. So our goal is to investigate on devices and to techniques that are enabled to proximity contactless interrogation of resonance sensor. So the proximity interrogation is useful when we consider sealed packages or hostile environment or volume that are not accessible. So you can imagine to go to the supermarket with smart devices to check if the food is good or not. So there's some application on contactless interrogation. So to enable contactless operation, we have that the cable solution are not allowed, and we need to use passive sensor because we are in presence of a hostile environment condition. And also we use the resonant principle because it's robust for contactless operation. So to do that, we need to have two units. The first one is the interrogation unit that is used to excite the sensor and to detect the signal that comes from sensor. It has to output a signal that is related to the frequency of the resonance sensor and to the quality factor. And of course, we need a contactless operation because we have no cables between the two units. And the sensor unit is composed by a resonance sensor and has to be passive. So we have no batteries inside, we have no integrated circuit. And to do that, we can consider the excitation and the detection phase simultaneously in time, but it is rather complex and critical. And it requires very complex electronics. So on the other hand, if we consider the excitation and the detection as separated in time, we can use a very simple electronics to measure the quantities of the sensor. So we propose here a contactless time-gated electromagnetic interrogation that can be used for passive piezoelectric resonance sensor. This is the block diagram of the system. We have high frequency resolution DDS signal generators that produce three signals, and we have analog switches that are used to switch from the excitation phase to detection phase. Then we have the first, the primary coil that are connected to interrogation unit, and the secondary coil that is into the sensor unit connected to the resonance sensor. And then we have the readout electronics on the detection phase that are used to amplify and downmixing the signal detected from the sensor. So in the excitation phase, we have the primary coil that is connected to the signal generator that excites the sensor. And due to the direct piezoelectric effect, we shake the sensor so we can transfer energy to the sensor. And I'd like to point out that the excitation condition of that we have the frequency excitation equal to the resonant sensor. The resonant frequency of sensor is not strictly required, but if you want to improve the signal-to-noise ratio during the detection phase, we can use a tuning algorithm to make this excitation frequency equal to the resonant frequency of the sensor. Now moving on the detection phase, the primary coil is disconnected from the excitation and the excitation signal is switched off. And then we have the sensor that undergoes to decaying oscillations. And so it produces an induced voltage that is proportional to the free decaying response of the resonator. So please note that this current on the primary coil is 0 because we have a very high impedance amplifier, and we have that the signal is then amplified and downmixed by analog multiplier and low-pass filter. So let me go deeper a little on the background theory of this system. So we have some assumptions. So we have a lumped element modeling of the sensor, and so we can change, we can represent the sensor by its BVD equivalent model. And so by making some assumptions, so we have no current that flows into the primary coil. So we have that this impedance has no influence on the readout signal that is represented from this equation. So also considering that the impedance of the secondary coil is negligible with respect to this impedance, and for very high values of Q, we have quality factor, we have that this equation comes to the sum of the damped mechanical response plus the damped electrical response. And please note that the frequency of the damped mode is equal to the resonant frequency of the sensor due to the high value of the quality factor. So again, we can consider that the damped electrical response can be negligible because it has a very faster time constant. So we obtain a signal at the primary coil that is related to the damped mechanical response. And again, please note that the mutual inductance that is related to the distance where we put the sensor unit does affect only as an amplitude scale of this signal. So we have now the downmixing part of the circuit. So we multiply the signal that we have seen before with a reference signal that is done because we have we achieved to read out signal that has the same characteristic for the damping, but it has different frequency, and the frequency of the output signal is the difference between the frequency damped mode and the reference signal. So we can tune this output frequency and shift in the range that is compliant with analog to digital converter. It's very important to have a very common analog to digital converter, so with not high sample rate. And then if we want to estimate the frequency output and the quality factor, we have used an autocorrelation analysis block that calculates the autocorrelation waveform that is represented here, and this is the formula of the autocorrelation. And by simply measuring the distance between peaks, we can achieve to information of the frequency output of the signal. And also by interpolated these peaks with an exponential curve, we achieve to a damping factor that is related to the quality factor of the sensor. So we have done some design and optimization of the coils that we used for the primary and secondary coils. And here is represented a simulation and experimental results given by two identical spiral coils with characteristics that are represented here. And so we see a very good agreement between the simulation results and the experimental results. And as expected, we have that the mutual inductance decrease with increasing of the distance. So it decreases the amplitude of the detected signal. So we have also evaluated the effect of the coils misalignment and different diameter of the coils. And we have found that by increasing the inner diameter of the module inductance, it becomes less sensitive to the coil misalignment. Of course, we have to take into account that there is a trade-off between the dimension of coils and the interrogation distance. So we don't make some big coils to have a portable system. So it is a picture of the prototype that we have developed, and we can see here the analog multiplier, the analog switch, the DDS that used for generating the signal. Is the list of the components used to assemble the prototype, and here is represented the primary coil and the secondary coil connected to the Quartz Crystal Resonator. So you have here some validation of the principle. So we have used one Quartz Crystal Resonator, and we have taken some reference measurement with the impedance analyzer in order to achieve to hit resonant frequency and quality factor. So then we put the sensor unit near the interrogation unit, and we achieved to this decaying response of a resonator. So if we have that behavior that is expected because we have an exponential decaying response of the resonator. So by multiplying the signal from this reference signal, we obtain the output signal that has the frequency that is the difference between the damped mode and the reference signal. So we have developed a Labview program in order to acquire the signal and to calculate the autocorrelation analysis block. And here is represented the picture of the control panel. So we have here the acquired gating and output signal. And here we have represented the superimposition of the demodulated decaying resonance, that is all of these responses. And here is the calculated autocorrelation signal. From this autocorrelation, we can estimate the frequency of the damped mode of the resonator and the quality factor. We have now done some experimental by varying the distance between the interrogation unit and the sensor unit. And as we shown here, we have that the estimated frequency and the quality factor are not affected by the distance d. So we have a very little dispersion of the values by repeating measurement, and we have no influence of the varying the interrogation distance. We have then compare the reference and the estimated values for this kind of sensor, and we have found that it's a very good, we have the very good agreement between the estimated frequency and the reference frequency, and also for the quality factor here represented by varying the distance and with the reference values that's shown here. Then we have used other sensor in order to validate the principle by changing the resonance sensor, and again we obtain a very good agreement between the reference and the estimated values. So the deviation of the frequency it's less than 100 ppm, and for the quality factor we have a low percentage of points of deviation. So in conclusion, we have proposed a technique for electromagnetic interrogation of QCS sensor. That technique is based on the separation in time of the excitation and the detection phase, and as in the first order independent on the interrogation distance d. So we have validated the principle and demonstrated it that for distance up to 20 millimeter. So we can think that the concept can be used for the realization of smart sensing labs in order to measure the conservation of food and drugs into sealed packages or for biochemical application. And the ongoing activity is to testing the system with other different kind of sensors, not only to Quartz Crystal Resonator, and to develop a standalone interrogation unit, because now we use a personal computer to make the autocorrelation analysis. So we now think to move to DSP and so other devices. So that's conclude my presentation. Thank you very much for your attention.